Okay, thank you, Alvaro and the other organizers. It sort of pains me to say this, but probably it will be better if the questions come after the talk. The format seems pretty challenging for me to see that people are asking questions, but I would love to get questions at the end. Okay, so let's get. Oh dear, hold on a second. Uh, yeah. Okay, so let's get started. So uh, the one way to come at this, the what I want to talk about is the very important topic of torsion subgroups of elliptic curves over number fields. So suppose you have an elliptic curve over a number field. Then it has a Mordell-Weil group, which is the group of all rational points. And by theorems of Mordell and Weil that are about 100 years old now, the torsion subgroup is finite. By a much recent and bigger theorem of Morel from 1996, not only is the torsion subgroup finite, but as you vary over all elliptic curves over all number fields of any fixed degree, then still the size of the torsion subgroup is uniformly bounded, or equivalently only finitely many torsion subgroups arise as you look over all elliptic curves over all number fields of any fixed degree. So that naturally motivates the question, if you fix a degree of a number field, can we completely classify all the possible torsion subgroups in each degree? Well, yes, if D is equal to 1, so this was the beginning of this sort of modern story. So in other words, Mazur in the 70s classified all possible torsion subgroups of elliptic curves over the rational numbers. There are 15 possibilities. Then for D equals 2, in other words, as we vary over all elliptic curves over any and all quadratic number fields, then the torsion was classified by Kamieni, Kenku, and Momose in the 80s and 90s. And then already for D equals 3, in other words, as we vary over all cubic number fields, this is very difficult. So the answer was announced in 2016 by these people. And it's my understanding that a complete preprint is not yet available. So the sense that you get is that this is quite a challenging problem to completely classify the torsion subgroups of elliptic curves over degree D number fields. And so you could just work harder, but a lot of myself and a lot of other people are interested in certain ways of simplifying the problem or studying part of the problem where you can say a lot more. And so I want to talk about the CM case, elliptic curves with complex multiplication. The definition will be coming soon. And again, the work that I'm describing today should lead, in some sense, you can ask me about that after the talk if you like, to a complete solution of the classification of degree D torsion subgroups of elliptic curves with complex multiplication. So that's the first sort of motivation from the torsion angle. Now I want to motivate it in a different way in terms of modular curves. So suppose I have a modular curve over the rational numbers. Again, later it'll become clear exactly what I mean by that, but you have these familiar families of curves, x naught of n, x1 of n, x of n, xm of n. Okay, so each modular curve is parameterizing an elliptic curve together with some kind of additional level n structure, complete or partial. And so by taking your elliptic curve together with level n structure and forgetting about the level n structure, but retaining the elliptic curve, you get a map, a finite degree map down to the moduli space of all elliptic curves, which is just the projective line. And so if I give you a closed point on the J line, which is basically the same as you would give me such a point by giving me an irreducible polynomial over the rational numbers, I would like to understand the fiber of this map over that particular J invariant. And if that sounds too fancy and too scheme theoretic, I want to say that really this is just a special case of the most classic problem from algebraic number theory. If I have a finite degree extension of Dedekind domains and I have a prime ideal downstairs, I would like to understand how it factors in the upstairs Dedekind domain. Because if you remove the point at infinity and then the preimage, then we have nice affine curves, and so the coordinate ring is, each case is just an extension of Dedekind domain. So you can really think of this as just being an algebraic number theory 1 type problem. Okay, so we're definitely going to remove infinity because that's a cusp. Later on, I'm going to remove j equals 0 and 1728 anyway. Those are the only ramification points. So away from that, what are you trying to do? You're just trying to figure out how many upstairs primes you have lying over your downstairs prime. And for each one, you want to figure out what the residual degree is, the F in the sense of algebraic number theory. And here, because the downstairs prime sort of has its own residual degree, so the residual degree in the relative sense would be the degree of the residue extension P, which is a closed point on the upstairs modular curve, divided by the degree Q adjoin J. But if we think of J as known, then it would be equivalent, of course, just to determine D of P. So the degree of this the residual degree of this point on the modular curve. So to sort of understand the fiber, we'd like to know the number of closed points and what the residual degrees are. One minor difference between this case and the most classical case where you just have an extension of number fields, well, in the classical case, the residue fields are just finite fields. And so if you have a finite field and you know its degree over some other finite field that you know, well, then you know the finite field up to isomorphism, but that's not true for number fields. So it would be really great to not just know the degrees of these closed points on these modular curves, but actually to know the residue field here, which is the field of moduli of the corresponding point on the modular curve. Okay, so that's sort of a second way of getting at this basic problem, and this is a relatively short talk for me, so I just want to pay some lip service to the fact that whenever you study these sorts of things, there's this beautiful sort of triple intersection among torsion subgroups of elliptic curves over number fields, which we saw, points on modular curves, which we saw, and Galois representations on elliptic curves, which we are not seeing today, although it's certainly very important. Okay, so again, I really want to work in the CM case, which simplifies things considerably. And just to shout out here, so this was really the study of this was initiated by work of Alice Silverberg in the late 80s and early 90s. In particular, she proved the uniform boundedness of torsion in the CM case first before Morel proves it in the general case. And then my collaborators and I, Abby Borden, Paul Pollack, Jim Stankiewicz, we've been working on this for about 10 years now, and so we're definitely making progress. And another person who is making important progress is one Alvaro Lozano-Robledo, who has some really important recent papers on the subject. Thanks to all this work, we're actually getting close to complete answers to either of these two questions. Well, if we're getting close, let's really try to get closer. That's what we want to do. So I think that within within relatively soon, we should actually be able to finish off the CM case. And so the talk that I'm presenting is a step towards that. And again, because I'm not really talking about Galois representations so much today, I definitely need to mention there's a very important, very long recent paper of Alvaro where he gets very strong information on the Galois representation for the Mod-N Galois representation and also for the L-adic Galois representation if you're over Q adjoin J, so the minimal possible field of definition. That definitely tells you a lot, and it's my understanding that he has a sequel paper which should do even more. And if you had perfect information about the Galois representation of a CM elliptic curve, then in principle you would be able to answer most or all of these questions as well. So that's certainly an important perspective. But today I'm going to be talking about the sort of the modular curve perspective. Okay, so what's complex multiplication? If you have an elliptic curve over the complex numbers, you can write it as C modulo a lattice, and then the endomorphism ring from this perspective is literally just the set of complex numbers that stabilize the lattice. And the two choices are either the only complex numbers that do so or the integers, which is what happens most of the time. And then the only possible case is that this endomorphism ring is an order in an imaginary quadratic field. And in the latter case, we say the elliptic curve has complex multiplication. Okay, so for this talk, we have an imaginary quadratic field. So Q adjoin the square root of some negative number. Delta of K is going to be the discriminant of the field. In other words, the discriminant of the ring of integers of the field. So ZK is the ring of integers. On the other hand, so that's the maximal order in the imaginary quadratic field, but the endomorphism ring could be any order. we're very lucky that for quadratic fields, the structure of non-maximal orders is very simple. For each positive integer, there is a unique order which has index f just as an additive subgroup of the ring of integers. Okay, so this f is called the conductor, and then this order gets a discriminant as well, and the discriminant is f squared times the fundamental discriminant. Okay. And so in general, I will identify knowing the discriminant is the same as knowing the order. And so we'll say the elliptic curve has delta complex multiplication if its endomorphism ring is the unique imaginary quadratic ring whose discriminant is delta. Okay, and so now the thing to realize is that you're probably most familiar with the class number 1 case where the J invariant is defined over Q, but that's only 13 J invariants. There's infinitely many CMJ invariants, but their degrees go to infinity. So what's true is that if you fix the discriminant, or equivalently if you fix the endomorphism ring, you have finitely many J invariants, more than one usually, but they form a single closed point, which I'm calling capital J delta on the modular curve, but the residue field of that closed point is not going to be Q. Usually, the degree of that closed point is going to be the class number of the order, which is the size of the class group of the order. Okay, so I mean, maybe you're not used to thinking about it in terms of closed points, but so this is just a reminder on the sort of standard correspondence between closed points and f-valued points on a scheme, but it may not be what you were expecting. So how do you think about this? So the closed point is really just corresponds to a single complete Galois orbit. So another way of saying this is that there is an irreducible polynomial over Q called the Hilbert class polynomial of discriminant delta, whose roots are all the delta CMJ invariants. So they form a complete Galois orbit. And so the closed point is basically the Galois orbit itself. Okay. And then the closed point consists of H of delta individual J invariants. Okay, so these J invariants are just Galois conjugate algebraic numbers, each of degree H of delta. Okay. And so within this package of Galois conjugate algebraic numbers, there's sort of a favorite one, or my favorite one is little j sub delta. This is corresponding to the elliptic curve, which is uniformized by O itself. So it's pretty clear that the endomorphism ring of C mod O is O. So that's my favorite OCM elliptic curve. Among other reasons that this is nice, this particular J invariant is not just a complex number, it's actually a real number, and we'll see soon why we care about that. Okay, so now I want to talk about recent work with Abby Borden. So if I take a pair of positive integers, m dividing n, so this work is looking at the fiber of the modular curve xmn. You'll see in a second, but this is parameterizing z mod n cross z mod n torsion. And so we do this for any CMJ invariant. What do? We compute the least degree of a closed point on xm of n, okay, for any given CM discriminant delta. So we have two papers. The first paper does this over K, the imaginary quadratic field, which is easier. And the second paper does it over Q, which is what you really want. And that is a bit more technical. Okay, on the other hand, when m is greater than or equal to 3, the blue problem and the red problem collapse, I guess, into a brown problem, because if you have full m torsion when m is at least 3, then it turns out that you have to have the imaginary quadratic field in your field of definition anyway. But really for this talk, I want to concentrate on m equals 1, so I just have 1 point of order m. Okay, so one thing that we find is that when we're working over K, looking at the fiber of this map as a map of curves over the imaginary quadratic field K, then not only do we find the degree of the least closed point, but it turns out that the degree of every closed point is a multiple of the degree of the least closed point. I'll say why that's important in a second. And then we also show by examples that this may not be the case when you're working over the rational numbers. Okay, so why does this matter? Again, the moduli interpretation here is that if you have a number field and you have a delta CM elliptic curve defined over that number field, so that inside the torsion subgroup of that elliptic curve over that field, you have the group Z mod M cross Z mod N, then that induces a closed point on the modular curve, and an embedding, therefore, from the field of moduli, the minimal possible field of definition for this structure, into the field F. And conversely, you can always take F to be Q of P. But now if you look at it on the F rational point side, you say, okay, well, if I have this structure over my elliptic curve over F, if I just extend my number field F to any other number field, then the degree gets multiplied by whatever positive integer I want. And the number field is big, it's same elliptic curve over a bigger field. So I still have this torsion structure. So if I'm looking at it on the side of sort of F rational points, if I'm interested in trying to find the set of degrees D for which, for my fixed delta, I have a delta CM elliptic curve and Z mod M cross Z mod N torsion inside that degree, well, that set of degrees is closed under passage to multiples, whereas the set of closed points is not closed under passage to multiples. There's only going to be finitely many, it's a finite fiber, so there's only going to be finitely many closed points. And so this, okay. So this says that really what we want to do is we would like to know the degrees of all the primitive delta CM closed points. So by primitive, I just mean its degree is not a multiple of some other closed point, because then on the F valued side, we don't need to know it. So we can get away with knowing just the primitive degrees of delta CM closed points. And that's equivalent to understanding precisely which number field degrees you have a delta CM elliptic curve with torsion subgroup C mod M cross C mod N. Okay, so that was a very important equivalence. And so again, so after the work with Abby Borden, when M is greater than or equal to 3, as I said, we only have this one primitive degree because every other closed point has degree dividing it. But when M is 1 or 2, we know the least degree, but we don't know, the work doesn't give all primitive degrees. Not quite. It gives it up to a factor of 2, which we're fighting about. Okay, so if we're trying to classify the CM torsion in degree D, we still have to do x1 of n, so 1 point of order n, and we still have to do a point of order full 2 torsion and another point of even order. And today I'm just going to concentrate on the case where you have 1 point of order n. Okay. And so now let me transition to the work that I want to talk about today. And so now I'm going to make an important simplifying assumption that K is neither of these two fields, which maybe your two favorite imaginary quadratic fields, or maybe your two least favorite imaginary quadratic fields, depending upon what you're doing. I should say that for all the work described above, we were not making this simplifying assumption, and you have to do more work in order to get those cases out of it. But for the work that I'm going to describe below, at least in the way that I'm describing it now, I am making use of that simplifying assumption. Okay, so let me make immediate use of this assumption. And now I want to look at the map from x1 of n down to x naught of n. So x1 of n is parameterizing elliptic curves together with a rational point of order n, and x naught of n is parameterizing elliptic curves together with a rational cyclic subgroup of order n. So again, there's a forgetful modular map where you just take your point of order n and you associate to it the cyclic subgroup that it generates. Okay. And so it turns out something amazingly simple happens, that, again, if you exclude these two imaginary quadratic fields, then the fiber over every single closed CM point on x naught of n is completely inert in x1 of n, which means what you think it means from algebraic number theory. So over each downstairs closed point, there's exactly one upstairs closed point, and there's no ramification. And so therefore, the degree of the corresponding field of moduli, the upstairs degree, is equal to the downstairs degree times the degree of this covering map, which is phi of n over 2. So what does that mean? It means that there's just a complete equivalence between the problem of knowing all degrees of delta CM closed points on x1 of n is the same as knowing all degrees of delta CM closed points on x naught of n. Okay, and so again, before we knew the least degree of a delta C. This equivalence couldn't be easier. Whatever your degrees are on x naught of n, you just multiply it by phi of n over 2, and you get the set of degrees here. And so previously we knew the least degree on x1 of n, so okay, we divide that by phi of n over 2, and we get the least degree on x naught of n. So the previous work was sort of working with x1 of n, although actually secretly we were working with x naught of n in order to do x1 of n, and we were deducing consequences for x naught of n. And so I want to reverse this. And so the main result that I want to talk about today is that if you fix your delta, again, with this simplifying assumption that the fundamental discriminant is not -3 or -4, what do I want to do? I literally just want to tell you what the fiber on x naught of n is over every delta CMJ invariant. And again, in the strongest possible sense that I really will tell you, or the work really will tell you what the field of moduli is and not just the degree. And so actually getting the field of moduli, I think, is an advantage of this particular approach. Okay. So that's the main result. I'm trying to compute fields of moduli, all the closed points in x naught of n with a single CM J invariant delta or closed point, and I want to compute completely the fibers over those points. Okay, so let's get started on how we would do that. So suppose I have an isogeny of elliptic curves a priori over the complex numbers. So this isogeny has a field of moduli. For instance, it induces a point on, suppose it's a cyclic n isogeny, and so it induces a point on the modular curve x naught of n, and so that point has a residue field, and so it has a field of moduli. And so in principle, what do we want to do? For every CM cyclic n isogeny, I want to compute the field of moduli, and then I want to collate them. So, I mean, a very easy observation is that if your isogeny is defined over a certain field, then your source elliptic curve and your target elliptic curve had better each be defined over that field, and therefore the field of moduli of the isogeny certainly contains the field of moduli of the two elliptic curves. And so strange, I had never seen this observation before. Maybe afterwards someone can tell me where this observation occurs in the literature. It can't be new, but a half-page argument or so shows that if your elliptic curve does not have complex multiplication, then this kind of very obvious lower bound is always an equality. So in the absence of the CM case, the field of moduli of the isogeny is literally just the compositum of the field of moduli of the two J invariants. And you can also give easy examples to see that this is not necessarily the case when you have complex multiplication, but it's really close. And that will come out in the analysis that we're doing. Okay, so to move on, again, I have my delta. I'm kind of viewing my imaginary quadratic field as being fixed here for what we're doing. And so the notation is sort of suppressing K. And so now I want to define a very important field. I'm going to call it the rational ring class field. So this is literally just Q adjoined my favorite CMJ invariant with discriminant delta, my little j. So there it is. Okay, so the the K is fixed, so I'm sort of indexing it by the conductor. So this is the rational ring class field. Okay. That name is not super standard, but again, this is the number field that is generated attached to the Hilbert class polynomial of discriminant delta, so it's definitely a known number field. More famous is the regular ring class field, which is exactly the number field that I took before, only I adjoined K. So the ring class field has a big part in class field theory. It's a abelian Galois extension of K, et cetera, et cetera, et cetera. Okay, but so since Q adjoined J is the rational ring class field, it's sort of obvious relevance to what we're talking about right now. And the rational ring class fields for fixed K form a very nice directed system in the conductor. If you take the compositum of any two of them, which seems to be what we want to do here, then it works out, if you're in a position to have a guess for what the compositum of the two rational ring class fields should be, then it's exactly what your guess would be. It's again a rational ring class field, and it's just the conductor is the LCM of the two rational ring class fields. And so it kind of looks like we already computed Q adjoin J of E comma J of E prime, but we didn't. There's a algebraic number theory snag here. And the snag is that I didn't say that this rational ring class field is Galois over Q. And in fact, I'm telling you that it isn't, definitely is not, except in finitely many cases. Well, why does that matter? Well, I chose my favorite Galois conjugate, little j, and if the field was Galois, it doesn't matter which one I chose. They're all of the other roots of the Hilbert class polynomial are going to lie in the same field. If it's not Galois, yeah, it really matters which one I choose. Okay, so it turns out though that this is not so hard to resolve. The regular ring class field is well known to be Galois, usually not abelian, but always Galois over Q. And so if you think about it, the Galois closure of your number field is the intersection of all the finite Galois extensions of your field. So, I have a field which I'm telling you it probably isn't Galois, but it sits inside a Galois number field of index 2. And so therefore, if it's not Galois, its Galois closure has to be the ring class field. Okay, so a little more sort of algebraic number theory type stuff here. So it turns out that the number of real delta CMJ invariants is known. It's the two torsion, cardinality of the two torsion of the class group of the order of discriminant delta. That sounds kind of fancy, but believe it or not, over 200 years ago, Gauss gave a formula for the size of this group in terms of delta, or really just in terms of the prime factorization of delta. So this is really equivalent to the genus theory of binary quadratic forms. Okay, so it turns out that this means that, first of all, this means that the rational ring class field is Galois if and only if the class group is two torsion, which by a result of Heilbronn is only the case in finitely many, for finitely many delta. Moreover, if you have a delta CMJ invariant, when does it lie inside the field generated by my favorite delta CMJ invariant? Well, it lies in that field if and only if the second J invariant is also a real number, okay, which is kind of follows easily from what I just said. But so let me move on for time. So yeah, so this is basically just doing the Galois theory of the J invariants. Okay, so now we go on and do the elliptic curve applications. So first of all, it's kind of classical. I found this result precisely in a 1989 paper of Parrish, so it gives you an upper bound for the field of moduli of any cyclic anisogeny on a CM elliptic curve, uh, at least if you adjoin K. And so an upper bound is a larger ring class field. So the elliptic curve itself is going to be defined over the ring class field K of F, and all of its cyclic anisogenies are going to be defined over a bigger ring class field, K of F times N. Okay, so that's over K, and we want to work over Q, but it gives you an upper bound. Okay, and so now I just need to I want to tell you approximately what form the main result says. So if you have an elliptic curve, delta CM, and it has a cyclic, with a cyclic anisogeny, then the field of moduli is going to turn out to be a very simple field. It's going to be either a rational, here I mean isomorphic to, is isomorphic to either a rational ring class field or to an actual ring class field. And then the conductor of either of these two fields is somewhere between the conductor F that you started with and n times that. Okay, so the result is actually, I mean, we want to prove this, of course, but at least you're seeing that the fields of moduli that we're getting are pretty simple. Okay, and so then the next thing that you should do is you should reduce the case of an arbitrary cyclic anisogeny to the case where n is a prime power. And it should not be surprising that you do that, because in general, whenever you have an isogeny, you look at its kernel, which is a subgroup of a certain order. Like every finite commutative group, it decomposes as a product of its CELO L subgroups. And so you would expect that you should be able to to reduce to the prime power case without doing anything particularly heroic. And you can do that. It's slightly technical. It's not so interesting, and so I'm actually just not going to talk. I made some slides about it, but it's less interesting than the actual prime power case. So trust me that you can reduce the case of trying to understand the field of moduli and account for all the cyclic anisogenies. You can do that if you can do that with prime powers. Okay, so now we come to the fun part of the talk. So if you fix an imaginary quadratic field and you fix a prime and you're looking at prime power isogenies, now you're coming into the situation where you can deal with, you can use isogeny volcanoes. So for me, an isogeny volcano is a graph which is directed and is allowed to have multiple edges, whose vertices are the J invariants of elliptic curves over the complex numbers that have complex multiplication by some order in the imaginary quadratic field K, and the edges are basically just corresponding to L isogenies with a reasonable equivalence relation. So this graph is a directed graph, but in a very understandable way. Whenever you have an edge, you always have the corresponding inverse edge, and the inverse edge just corresponds to the dual isogeny. This graph is stratified. The vertex set is partitioned into a bunch of subsets indexed by the non-negative integers. And so those are called the levels. So for any vertex, you just record the power of L that divides the conductor. So that's a non-negative integer, and you call that the level. Okay, well, I want to say more about the structure of the isogeny volcano, but, oh, okay, I will. But so one thing is that the L power isogenies can change the conductor, they definitely can, but they can only change the L part of the conductor. So if you're studying this volcano, it's going to break up into pieces, which are parameterized by the prime to L part of the conductor. You may as well fix that as well. Okay, so let me show you some beautiful pictures of these isogeny volcanoes. So they have a pretty simple structure. So what's happening so there's the surface is the vertices at level 0, so where the conductor is primed to L. And so what's happening at the surface is the most complicated part, and it's the only part which is depending upon, for instance, how L is splitting in the CM field. So if L anyway, so every vertex has outward degree L plus 1, because that's how many cyclic L isogenies you have coming out of any elliptic curve. Right. And so we'll call there's three types of edges, horizontal, ascending, and descending. The horizontal edges are the edges that run between surface vertices. Okay, and so if L splits in the CM field, then every surface vertex has two outward horizontal edges. If L ramifies, every surface vertex has one outward horizontal edge. And if L is inert in the CM field, then there are no horizontal edges. Okay, that's taking into account what's written down there. Then the other types of edges are ascending and descending. So if you're in a level which is below the surface, so level L greater than 1, there's always a unique ascending edge from your level to the next higher level. Okay, so you can see that. And then there are descending edges, and the descending edges are literally just the inverses of the ascending edges. And so that accounts for absolutely all of the edges on the isogeny volcano, and really it tells you the entire structure of the isogeny volcano, except for more precise information as to what's happening on the surface, which is actually not necessary for what I want to do. But yeah, so every vertex that's not on the surface has a unique ascending outward edge, and from all this information you can deduce the number of descending outward edges coming from each vertex. If you're away from the surface, then every vertex has precisely L descending vertices. This is an infinite graph, by the way. I cut it off at level 2, but it keeps going down. And here again, I'm trying to do something generic, but if you're following me, here L is equal to 2 for the pictures that I'm drawing. At first, 2 is a little anomalous for the analysis, actually. So at first I drew L equals 3, but that was too many edges. Okay, so you have this isogeny volcano, which has a well-known structure. And now the usefulness of the isogeny volcano is coming from the fact that cyclic L to the A isogenies between these CM elliptic curves, which is exactly what we're trying to account for and keep track of the fields of moduli for, well, they correspond bijectively to length A non-backtracking paths in the isogeny volcano. What is backtracking? A backtracking path would mean if you traverse an edge and then you immediately follow it with the inverse edge. And if you think about it, that means you do an isogeny and you do the dual isogeny, and that's going to stop your L power isogeny from being cyclic. Okay. So really what we need to do is we need to, we sort of start with some vertex at some level C, and then we fix an A, and we just want to find all the paths of length A in the isogeny volcano, starting from that vertex, and for each such path, we want to figure out what the field of moduli is, okay? So the first thing that we have to do is we have to sort of count all the paths, non-backtracking paths of length L to the A, starting from a particular path. And that sounds like it, in a general graph, that might be tough. But the isogeny volcano has a very restricted structure. Here I'm just impressionistically drawing some paths for you. This is not an exhaustive picture of anything. The length of all these paths isn't even the same, I think, if you check. But so it turns out that the paths are restricted. They're allowed to have an initial ascending part, although they need not. This one does not have an initial ascending part. But you can only ascend at the beginning, and then once you're done ascending, if you're at the surface, which you might not be, and if you have surface edges, which you might not have, then you can have a horizontal part. You can't have a horizontal part if you're inert. If you're ramified, you could only have one horizontal edge. But if you're split, you could have as many horizontal edges as you want. So there's a middle part, which is horizontal, if you have it. And then the final part of the graph, the path has to be descending, and you can always descend as much as you want. Okay, so basically you have to count the number of ways to go up, and then go over, and then go down. And so you can count them without too much trouble. So using this information, we can already compute the field of moduli over K, so that's always easier. So again, just suppose that the source elliptic curve level C, so the power of L conductor C, the target elliptic curve as level C prime, and let's let capital C be the larger of the two. And then in this case, if you do K, then everything is Galois, and these K adjoint J's are just ring class fields. And then one of the merits of reducing to the prime power case is that one of the two ring class fields is going to contain the other. And so that's the point. So whichever one is bigger between C and C prime, the compositum here is just going to be K adjoin this. So so the field of moduli is going to contain this this ring class field, at least if you throw K in. And then using this theorem of Parrish that I showed you before, it's not hard to see that you have the other containment. So the field of moduli of any cyclic isogeny, if you work over K, this was probably, I believe this was known before, it is just this corresponding ring class field where you keep track of the level that you started at and the level that you ended at. Okay, so this is still a non-trivial counting problem to count all these things, but you can do it. Okay, so now we want to work over Q, right? And so right, so you can because of the Galois symmetry, the class group is acting transitively on all the vertices in the isogeny volcano of a fixed level. And so you may as well assume that your source J invariant is your favorite J invariant, little j of delta. You cannot assume that your target J invariant is your favorite J invariant, but you can assume that your source J invariant is. And then to simplify things, why don't we assume that the level at which we end in our path is no deeper than the level in which we start? Why can we assume that? Well, for instance, if it were the other way around, we could just reverse the path, okay? But reversing the path would correspond to the dual isogeny, which has the same field of moduli. So we may as well assume that we start out at least as deep a level as we end up. Okay, and then you sort of see where we are, and you see that well, we just said that we just computed the field of moduli over K to be this ring class field, and then again, just the fact that that it contain the Q adjoin J is just this ring class field, and so you see that we just have a simple dichotomy. The field of moduli is either going to be this ring class field or this rational ring class field, and so the only question is whether it contains K. And in brief, how do you decide whether the field of moduli contains K? You decide that by looking at the action of complex conjugation on the isogeny volcano. So it does act on the isogeny volcano. Just basically the action is determined by the vertices, and so the vertices are literally just complex numbers, and so your vertex is fixed if your complex number is a real number, and let's call the path real if all the edges are fixed under complex conjugation. And, eliding some details for time, of course, it turns out that whether your path in the isogeny volcano is fixed under complex conjugation is exactly the dichotomy that you're looking for. So your field of moduli is going to be the rational ring class field if your path is fixed under complex conjugation, and it is going to be the compositum of that with K if your path is not real. Okay, so in order to implement this, you actually have to figure out what the action of complex conjugation is on the isogeny volcano. That sounds like fun. I did it. I knew I wouldn't have time to tell you about it, but I did do it. That's something to talk about. One thing is that here, when L is greater than 2, the way the action works, the complex conjugation works, is different from the way that it is when L is equal to 2. It's actually a bit more complicated when L equals 2, and that complication kind of shows up in some prior work of Abby, Borden, and myself. And then finally, okay, so you do this, and now for any individual path, you have computed what the field of moduli of the path is, and now you have to go back and you have to solve the same accounting problem. So I didn't emphasize this, but again, you have to go back and forth between like the F-valued points, the J invariance as complex numbers, and the J invariance as closed points. So what that really means is that you have some equivalence relation on these paths, and certain classes of paths are going to correspond to the same closed point. And so you have to solve that counting problem. And by the way, this is actually some work here. I've done most of the cases. I still need to write down a few of the other ones. And you just get a set of tables recording all the possible fields of moduli for each of the parameter values. And these tables are probably going to fill about 3 to 5 pages in the end. But then you get the complete answer, and you should be able to use that answer to feed back into the study of the torsion subgroup. And I hope to have a preprint available with all this by the end of the month. And I'm done. So thank you so much for listening, and thanks to the organizers for organizing the talk.